Okay, let's try and finish this up. Right at the end of the last video, I got interrupted right at the end. We noted that the current in the circuit in this case would be 0.05 if there was a 6 volt drop across all 3 resistors. And just to prove this to you, here's our circuit with all of these resistors, 20, 40, and 60, a 6 volt battery. If I do go ahead and connect the wires, we see, oh, I got them reversed. Oh, that was one thing I did want to point out. If you have the wires reversed, maybe I did already point it out, it's just -6. So remember, the black one, the black probe goes at the end, at the far end of the object for which you want to measure the voltage drop. The red one goes before. Okay, so anyways, we found a 6 volt voltage drop across the whole thing. Notice it's the same as the voltage drop for the battery, and the equivalent resistance was 120 ohms. We see that the current is 0.05 amps, just as we predicted. So, what we're going to do now, instead of looking at these in isolation, is look at something a little bit more interesting, entire circuits, and how to analyze them all at once, not just little pieces of them. So, for this, let's see here. Okay, there we go. So, let's look at this first one. We have a series circuit. We know it's a series circuit because there's only one path for the current to take. It appears that there is a battery that has a voltage gain of 6 volts. Has a voltage gain of 6 volts. There are 2 resistors. R1, that's a 1, is 80 ohms, and R2 looks like it's about 90 ohms. So it says for this circuit, determine Req, or equivalent resistance, the current, the voltage drop for the 80 ohm resistor, the voltage drop for the 90 ohm resistor, the total voltage drop of the circuit, and we're told to place a voltmeter where it could measure the voltage drop across the 90 ohm resistor, and place an ammeter to measure the current. So, there's a lot of stuff to do here, and you might be a little overwhelmed. I kind of treat this, or problems like this, sort of like, if any of you have ever done like a Sudoku puzzle, where if you look at everything all at once, it looks very overwhelming, but if we do it piece by piece, it actually becomes pretty easy. We just kind of pick what we would like to do first, and what would be easiest, and we build from there. So for this circuit, let's determine, it's actually easiest to determine Req here. This is a series circuit, and we know that in series circuits, the equivalent resistance, the resistance of the entire circuit, if we were to pretend that all of the resistors we combine them into one big resistor, the equivalent resistance is really easy. All we have to do is add R1 and R2. So let's do that. Req equals R1 plus R2. So therefore Req equals 80 ohms plus 90 ohms. Req is 170 ohms. Got that one done. Now let's look at the current. Well, we know the Req. We also know the total voltage drop for the entire circuit. It's equal to the voltage gain for the battery. So we can use Ohm's law in regards to the entire circuit. That's the nice thing about Ohm's law, is it applies equally to entire circuits, as well as just pieces of circuits, individual pieces or combined pieces. So if we want the total voltage drop, that's going to be equal to the total current times Req. The total voltage drop here is 6 volts. Req is 170 ohms. So all we're going to do is take 6 divided by 170. We get that the current is approximately 0.035 amps. We're going to keep going. Voltage drop for the 80 ohm resistor. If I want the voltage drop for the 80 ohm resistor, I can find that using Ohm's law. Whereas this time I'm solving for V80, the voltage drop for just this one, is equal to, well, the current in a series circuit is the same everywhere, and we just found that, 0.035 amps, multiplied by the resistance of 80 ohms, and we get the voltage drop for the 80 ohm resistor is 2.82 volts. And again, remember what this means. Voltage drop means some energy is lost there. 2.82 volts means for every coulomb of charge that passes through, 2.82 joules of energy are given off. Now, finding the voltage drop for the 90 ohm resistor can be done the same way. Voltage drop for the 90 ohm resistor. We have the same current because it's a series circuit. We have the same we have the 90 ohm resistance. Okay, 6 by 170, so there's the current times 90. We get approximately 3.18 volts. So that's this, and this. Now, the total V drop of the circuit, remember, we already know this. We already know that it's 6, but let's prove that it's 6. We know that the total voltage drop must be equal to the voltage drop for the 80 ohm resistor plus the voltage drop for the 90 ohm resistor. And that ends up being 2.82 volts plus 3.18 volts. And if we do 2.82 plus 3.18, look what we end up with. 6 volts. So just like a Sudoku, your answers should check out. You should be able to actually check your answers as you do this. Okay? That should work. You should be able, your answers should all make sense, in other words. Another way of saying it. Last two things, place a voltmeter where it could measure the voltage drop across the 90 ohm resistor, and place an ammeter to measure the current. Let's do the last one. Ammeters in series circuits can be placed anywhere, because if we want to measure the current is the same anywhere. So here's how an ammeter looks. You remember the symbol for ammeter is given right here. And as you might have noticed in our simulation, in order to put an ammeter in, it needs to be wired directly into the circuit. So we can just kind of put a little circle here, label it A, and that's our ammeter. Voltmeters are different, okay? So ammeters go directly in circuits. Voltmeters are different. Voltmeters have to be placed kind of around what they are measuring the voltage drop for. So a voltmeter would look like this. Remember, the symbol is a circle with a V. And you kind of have to have, it has to be, imagine these are the probes. The probes go around the resistor, but you don't just write a V on a line like this. That would not work, actually. It wouldn't tell you the voltage. Matter of fact, there's a very good chance that if you wire up a voltmeter, and especially an ammeter, the wrong way, you will break them, okay? And that's not good. We want to keep our voltmeters and ammeters around. So, voltmeters go around the resistor or the lamp or whatever you're trying to measure. Okay? Now, what I'm going to do is we're going to make all these measurements on the simulation. We're going to see that it comes out to be the exact same thing. So, I'm going to get a battery. We have a 9-volt battery. That's okay, but we want it to be 6 ohms. So I'm going to decrease that. We're going to wire this up so that we have a resistor, and then we have another resistor, and then it goes back to the battery. Okay, good. So there's our stuff. Let's see here. We want this to be an 80 ohm resistor. And we want this to be a 90 ohm resistor. By the way, the order of the resistors does not matter one bit, and I'll show you that in just a second. So let's test everything, okay? Let's first test the voltage drops for both resistors. 2.82 for the 80, just like we found, and 3.18 for the 90 ohm resistor, just like we found. Total voltage drop is 6, just like we predicted. And the current, again, notice how the voltmeter doesn't get wired directly into the current, or into the circuit, but the current does have to. This one is, oh, let me back up. This one is cheating. It's not really fair to use that one. And we get a current, just like we thought, of 0.04, which is 0.035, just rounded a little bit, okay? And if we go backwards, we take the total voltage drop of 6 multiplied by the current. We get, wait a sec, did I do that right? Voltage drop, current. No, we have to divide them, sorry. Total voltage drop divided by current, and it's not going to be exact because of the rounding. Matter of fact, it's a lot of rounding, so it's really not going to be exact. We get 150 ohms. It's supposed to be 170, but because the current got rounded so much, that is that's why that happened. One thing I do want to show you, like I said, the order does not matter. If I made this one the 90 ohm resistor, and I made this one the 80 ohm resistor, the current is still the same. Oh, it's just that the voltage drops end up switching. Okay, so there's our first. Let's do one more example. Okay. For this circuit, determine the current, voltage drop for number 2, voltage drop for number 3, REQ, R3. We're going to put a voltmeter where it can measure the voltage gain of the battery, and we're going to put an ammeter to measure current. Let's do those first. Those seem easy. Voltmeter to measure the voltage gain of the battery. Well, that's pretty easy. We just need to surround the battery with a voltmeter. Very simple. And to measure the current, we can do that anywhere, so I'm just going to stick an ammeter down here, because the current is the same everywhere. Easy. What might be a little bit more difficult is to figure out these other ones. So for this circuit, let's determine, what do we know? We got to look at what we know here. We know the voltage, we know the battery voltage, we know the resistance of 2. We don't know anything about 3. Resistor 1 seems to me where we know the most about it. We know the voltage drop, and we know the resistance. That means we should be able to measure the current through 1. And the important thing is, that should be the current through the entire circuit at every single point. So if I want to find the current through 1, which is the same as the current everywhere, 3 volts, I1, 1800 ohms. By the way, you should get used to getting very small currents. Okay, the currents are typically very small. And in this case, we see that it's 0.00167 amps. Okay, and I'm rounding that just a little bit. So now that we know the current, that's useful because, well, let's see. We know the current, we know the resistance down here. We should be able to use that same current, because it's a series circuit, the current's the same everywhere, and find the equivalent, and find, the voltage drop for number 2. And again, remember, I equals I1 equals I2 equals I3. All the currents are the same. So if we take that current, 0.00167 amps, and the resistance, 2400 ohms, times 2400, we get a voltage drop of 4 volts. Okay, so that's good. We could find the voltage drop for 3 right now, or we could find REQ. It really doesn't matter which, and there's multiple ways to do both. If I take the total voltage, and I say the total voltage drop has to equal V1 plus V2 plus V3, and I realize that the total voltage drop of all these resistors has to equal the voltage drop for the battery, well then that's 12 volts. I already know there's a 3 volt drop here. Okay, so a drop in voltage. There's a drop in voltage for this resistor of 4 volts. I can solve for V3. Turns out that V3 should be equal to 5 volts. So, in other words, what this means is that V3 is 5 volts. Now, I could have instead found the equivalent resistance right now, because since I know the total voltage, I can use the total current to find REQ. VT is 12 volts. I is 0.00167 amps times REQ. and we get that the equivalent resistance is very, very close to 7,200 ohms. Now, I now have two different ways that I can find R3. I could either use the idea that the equivalent resistance is equal to R1 plus R2 plus R3 from my reference tables, and do 7,200 equals 1,800 plus 2,400 plus R3, and solve for it that way. 7,200 minus 1,800 minus 2,400 is 3,000. Or we could do this. We now know the voltage drop for number 3. We know the current is the same that we've had the whole time. We can solve for R3, and you'll see that we get the exact same thing. There we go. Multiple ways to find the same thing. So, this has just been an example in how to solve a whole lot of things about series circuits. It's always good to go back and check your work and find ways that you can check the work and make sure everything checks out. I'm not going to do this one on the simulation because the numbers are a little bigger, like you might have noticed, and I think you've got enough information with that already. But yeah, this is series circuits. If you have any questions about how they work, please feel free to reach out, and until next time, have a nice day.